Next up is Dinesh Venkatesan.
Hello, everyone. So today we will talk about building a knowledge graph, behavioral knowledge graph using the eBPF's observability capabilities. Why knowledge graph? Because with the proliferation of data and compute power, the answers are everywhere. The trick is asking right questions. And knowledge graph fundamentally enables researchers to ask right questions when they analyze certain unknown samples. Knowledge graph is also good for handling complex data, and it has a flexible schema, and it automatically abstracts relationships between entities, and it is an excellent motivator for building causal inference solutions. Let's take a quick anecdote of truth versus fact. When we say 4 plus 2 is equal to 6, it is a fact, whereas the reverse is not a fact but a truth, because 6 can be equivalent to 4 plus 2 or 7 minus 1 or 8 minus 2, so on and so forth. So let's take a case study of Mirai botnet. Mirai botnet, out of the several techniques it deploys, one of the techniques is it generates a random alphanumerical string the very first time it gets executed, and it overrides the ARGS pointer array. It overrides ARGS of 0 value, so that the process name, when enumerated by tools like PS or top command, gets subverted. However, an analyst can go to /proc/pad and the status file to get the command line attribute, and it would still reflect the original name of the Mirai botnet when it was executed. In order to subvert that, Mirai botnet subsequently calls prctl syscall with pr_set_name with the same alphanumerical string that was randomly generated. So after this syscall is executed, the proc PID status file is also changed. And there are still ways like analyst can enumerate proc PID maps to get the loaded map file, but that is beyond the scope of this particular quick talk. So this is a simple POC code or part of the Mirai botnet code that actually showcases this functionality. And we will now use eBPF's all-seeing capability to trace all the syscalls. As you could see here, in this case, the Mirai also embodies a ptrace function to see whether somebody is tracing it. So if you use fundamental tracing tools such as strace, the flow will break here and the Mirai will escape from executing further. So let's use eBPF to trace all the syscalls and log them as triplets and consume them with free open source graph database such as Kale or Neo4j. And then we can also use Neo4j graph data science libraries. And in case of Kale, we can quickly write some graph similarity implementations to make sense out of the data produced by the execution of unknown binaries. Let's quickly see a demo. So as you could see here, we have already executed eBPF and executed all the unknown binaries so that eBPF has recorded all the syscalls. And we can also use uprobes to record user level functions as well. But for simplicity's sake, we are just mapping the syscalls here. As you could see visually, the similarity between these two samples. So this being the Mirai botnet POC, where you can see even though the process name has changed, they both share the same PID. And this particular POC, it fundamentally shares the anti-debugging trick, but not the PRCTL trick. We can use graph data science libraries to detect similarities, dissimilarities, community detection for unsupervised clustering. We can also use Scala to do the visual comparison, and we can implement so many other graph algorithms here as well, which we can talk about in a detailed blog. Thank you.
Thank you a lot, Dinesh. Amazing to see what is possible with BPF.